Log on, tune in, find out. Another good idea from Cambridge.
From the Inha University in Korea, and he will talk on enhancement of near-cloaking using GPT vanishing structures. But first of all, he would like to announce the next
Sorry.
AIP conference.
Okay, thank you. Thank you for introduction. Yeah, and thank you for inviting me. Thank organizers for inviting me here. Let me take this chance to announce this next conference, next AIP conference, which will be held in KAIST, not the King Abdullah Institute. It's a Korea Advanced Institute of Science Technology. And it is in the city of Daejeon, Korea. And the Daejeon is here. This is Seoul, and it's about 150 kilometers down of the Seoul. It's a big science city. So please come to Korea, please. My university is here, Incheon. So, yeah. Okay. So that's it for this. So this is what I'm going to talk about. So enhancement of the near-cloaking using so-called generalized polarization tensor vanishing structures. Okay. This is joint work with Habib Amari at the École Normale Supérieure and Hyeonbae Lee at the same university as mine, and Mi-kyung Lim at the KAIST, where the next conference, AIP conference, will be held. Okay. So this is the outline of my talk, and many people talk about this cloaking and the near approximate cloaking. Cloaking. So I'll just briefly mention it, and then I'll explain you what the generalized polarization tensors are, and then I'll briefly tell you how to use this generalized polarization tensor for imaging. Okay, and then how can you use it for the enhancement of the near-cloaking, and then I'll talk about the GPT vanishing structures. Okay, so this is a transformation of PDE. We already have seen in many talks. So this is the Dirichlet boundary bed problem. So given Dirichlet data, and the Dirichlet to Neumann map is assigning Dirichlet data to the Neumann data. Okay. Now this is maybe simple, but it is a very important. I think it's a very important observation that if F is a diffeomorphism of omega, and which is identity on the boundary, then if you push forward this conductivity, then Dirichlet to Neumann map doesn't change at all. Okay, it's identity. We already seen it. Eh? Okay. Now using this fact, this Greenleaf and Lassalle and Ullmann, they transform this punctured disk onto annulus, and then because this is pushed forward of the identity, the Dirichlet to Neumann map doesn't change at all. Okay, and then it turns out that this idea can be used for the electromagnetic cloaking, and Pandry et al. And Leonhard, is he here? I don't see him here. Okay, all right, and these people use this. The Leonhard's idea was slightly different, but Pandry's transformation is exactly the same, and they use the transformation for the electromagnetic cloaking, and afterwards, and this Greenleaf, Krylov, and Lassalle Ullmann, they did tremendous amount of work, produced a tremendous amount of work for this cloaking. Okay, now the minor point is that this after pullback of the push forward of this the identity 1 has to be singular. It is infinity in the tangential direction. Is it right? And 0 in the normal direction. I'm talking about 2 dimensions. So this Kohn, Shen, and Vogelius-Weinstein proposed kind of approximation of this. It's called the near-cloaking. Some people call it the approximate cloaking, and we call it the near-cloaking. And instead of the blowing up the single point, they blow up very small region, small disk. Okay, so let for small number low, let the conductivity to be gamma in this small disk, and 1 in outside of the disk, and use this similar kind of the transformation. It is blowing up the small region, and then because the push forward of the this conductivity by this map preserve the Dirichlet-Neumann map, and they proved that this Dirichlet-Neumann map corresponding to the push forward of this sigma is almost like the Dirichlet-Neumann map corresponding to 1, and the difference, the error, is low squared. Low squared comes from the dimension. Square comes from dimension. Okay. Now they developed this one to the acoustic cloaking, Kohn, Onofre, and Vogelius-Weinstein, and the Liu, and the Wen. Okay, and now the way we see this is that okay, other than the transformation, this is nothing. I think this is a simple way to see this is okay. Now I have the conductivity 1 here, and you perturb a little bit of this by small ball. Then what is the effect of this perturbation observed here? The effect is low squared. Right? That's it. And if you perturb single point, because this is a harmonic functions, if you perturb single point, it doesn't change at all. That's why you got the perfect cloak. Okay. Now, so our idea is that if you perturb a little bit here, but in very special way, so that the observation outside is very little, then you can improve the cloaking effect very much. So this is a result. Okay, if you coat, here is a small perturbation, like a Kohn et al. Kohn and Vogelius and these people did, and we coat it by some structure, and this structure is called the generalized polarization tensor vanishing structure. And if you coat it, then the cloaking effect enhanced like this. So if n is large, this is a tremendous improvement, I claim. Okay. Now I have to explain you what the generalized polarization tensors are, and what the generalized polarization tensor vanishing structure is, and I also have to explain you what the enhancement means. Enhancement means this, but I can show you this figure. This is enhancement. Which part is enhancement? This is a near-cloaking, and this is an enhancement. This is one of the authors, Mi-Kyung Lim at the KAIST. Okay. Right. So enhancement is done. Now I have to explain you what the GPT is. So this investigation start with this figure. As soon as we saw this figure, we started this program. And this figure is well known. It's called the Hsuin's neutral inclusion. Hsuin is the well-known scientist in the theory of composite, and what it is that there is a uniform field. Okay, And he put a very specially designed structure in here. And if you put you perturb this uniform field with this structure, the uniform field doesn't change at all. It does not perturb at all. It looks like it is perturbed, but this is computational error. It's not the perturbed at all. And he used this structure, and he put many of these to design the kind of composites he wanted. Okay, this is pretty well. This is 1963. So this reminds us of this what is Pandry's the figure. I mean, bending the waves and things like that. And okay, and what does this mean? I mean, this means that okay, this is exactly the GPT vanishing structure of the first order. Okay, what is generalized polarization tensor? General polarization tensor is this one. Suppose I have conductivity distribution. I have a shape. I have an inclusion, and the inclusion has conductivity gamma. And I have background, and I assume that the background has conductivity 1. Okay. Now there is a uniform field, and I perturb this uniform field using this inclusion. Then the perturbed field, perturbed potential satisfies this differential equation. And now you make an expansion far away at infinity. Make an expansion of this potential at infinity. Then the background potential is here, and A is the gradient of background solution. And there is a matrix called the polarization tensor. And then, so it is kind of this leading order term is the gradient of the background potential, which is a kind of dipole. And then it is polarized. And then this is the gradient of the green function. So it is spread out by the green function, the gradient of the green function. This is the formula. Okay. Now this is the polarization tensor, or generalized polarization tensor of order 1. So you see, this one doesn't change at all. What does that mean? That means this term is 0, which means that M is 0. Polarization tensor is 0. So Hessian's neutral inclusion is its polarization tensor is 0. 0 matrix. Okay. Then how about the higher order terms? Suppose the background solution, background potential is a harmonic function, entire harmonic function. And now you perturb it. Then we have so-called the multipolar expansion at infinity. And multipolar expansion is given by this. So it's exactly the the derivative of the background solution. I'm assuming that the omega has the central mass of the omega is 0. Then we are expanding it at 0. Taking derivative as 0, and then polarize, and then take a derivative of gradient. Green function. Okay, that's the formula. And this quantity is called the generalized polarization tensor. Okay. Or there are other ways to compute or to represent this polarization tensor using layer potentials, but this is better to explain today. Okay. I claim that this is so given a domain, there is a corresponding generalized polarization tensor. I'm claiming that it is like a eigenvalues, a sequence of eigenvalues. So I'm claiming that this is a geometric quantity. Okay, it represents the geometry of the inclusion. And what do I mean by geometric quantity? Okay, for example, if the B is an ellipse, like given by this, or ellipsoid, then and the gamma is constant, then the polarization tensor can be computed explicitly like this. if you tilt, you rotate this ellipse a little bit, then this matrix will be rotated. Okay? Now, so if you look at this formula, if you know the polarization tensor, then you can recover A and B, right? And then using that, you can represent this polarization tensor in terms of ellipse. Okay? All right. So what I mean is there is a one-to-one correspondence between polarization tensor and ellipse, as long as conductivity is fixed. Okay? Now, what is this? This is called the equivalent ellipse. Our shape, our shape is kite. Okay? Now you compute the polarization tensor and represent this polarization tensor in terms of equivalent ellipse. And this is the equivalent ellipse. So this shows that this equivalent polarization tensor represents kind of overall property of the shape. Okay. On the other hand, this is proved by Maria and myself in 2003. If we know all the generalized polarization tensor, then you can determine the shape uniquely. It doesn't matter how many components it has. Okay? You can determine shape uniquely, which means that this GPT has richer information than eigenvalues. Okay? In this case, if you know all the generalized polarization tensor, then conductivity doesn't have to be known. I mean, you can determine even the conductivity as well. Okay? Shape and the conductivity. Okay. Thank you. In this proof, it was constant, but I think in general case it is true. I believe. But in this proof, when we proved this, we were only interested in the constant conductivities. So now, if we know all the generalized polarization tensor, we can determine the shape and the conductivity uniquely. On the other hand, if we know the first order polarization tensor, we can determine the equivalent ellipse. Then how about the in between this? What kind of geometric information these finite order, the generalized polarization tensor carry? But we've been thinking about this, but it is really hard to analyze this by analysis. So instead, we decided to do it numerically. So start with the equivalent ellipse and change the shape to minimize this. It is kind of optimal control procedure. And in order to do to do minimization, we need to know the shape derivative. So we compute the shape derivative of the polarization tensor. So this is a shape deformation. And if we deform the shape like this, then the polarization tensor changes like this. And use this one to make a shape. Let me just skip this. Then we can, using this formula, this asymptotic formula, you can design the shape derivative, and then you can design the optimal control procedure. And we did this is a numerical. Using this shape derivative, this is a numerical result. So starting the initial guess is, I think, is quite important. Initial guess is very good. This equivalent ellipse is a very good initial guess. Okay, start with this initial guess, and we are using the generalized polarization tensor up to order 6, and after 6 iteration, it is approaching to this. See, this is so it is a reconstructing shape. So it must have very, very important geometric information inside. Okay. This is a figure 2 years ago. This has not been published yet, but it will appear in mathematics of computation soon. Okay. This is the shape is inclusion has 4 components, and the corresponding equivalent ellipse is this one. Okay. Now you iterate 6 times, then you end up with this. Now this is interesting, and this one also. There are 4 components, and you iterate it, and it's end up with this. It is trying really hard to get the shape, but unfortunately it doesn't change the topology because of our method. Okay, this one too. It is trying really hard, but it doesn't change the topology. So our question is, does generalized polarization tensor contains information about topology? Can you catch it? So we design level set method. Okay. Again, this is my favorite figure. It has we are using 6 the generalized polarization tensor up to 6, and it has 5 humps. Then it is trying to get the shape a little bit. But how many humps there are? 9 humps? Too many humps. So it doesn't change at all. Just stay at the equivalent, the first initial guess. And it doesn't change at all. He doesn't know what to do. Okay. So, I mean, in order to get these humps, probably we need the high, even higher than 6, the polarization tensor. But this is great. Recently, I mean, just a few weeks ago, a student of the Mi-kyung Yu implemented this level set method. This is 100 times iteration. Okay, but 100 times iteration, and it takes a few hours to get this figure. But that's not the issue here. Whether we can generalize polarization tensor catches the topology, and it does. It does. Using 6, say? Yes, we are using level set method. Okay, but what is important is that this generalized polarization tensor contains an information about the topology. Okay? That's very important message here. Okay? Okay. Now let's go back to the near-cloaking. As I said, this is Khan and those papers' result. And if you look at this Kahn's result, then you can look at it as an asymptotic expansion. Okay, so what was their conductivity? Conductivity is gamma here, and if the radius of this circle is low, then asymptotic expansion at infinity. This is kind of the far field far field measurement, and so we can use this asymptotic expansions. And if you use asymptotic expansions, then the perturbed field, the normal derivative of perturbed field, is the difference between this one and this one. This is unperturbed field, and the difference is given by gradient of the U background solution, which is kind of dipole, and polarized, and then gradient of the green function spread out by the gradient. Oh yes, yes. When the low goes to 0, right? That's right. Now the M is a polarization tensor of this circle of radius low, and the polarization tensor of the circle is given by this. Okay, so therefore the difference between these two are less than rho squared. That's it, and then transform it. Then you get the near-cloaking. Okay. Now, on the other hand, let me go back to this. Look at this formula. If this is the full asymptotic formula, suppose we can kill the like the Hessian's neutral inclusions. If you can kill the polarization tensors, first order, second order, third order, kill those you can design a structure which kills the polarization tensors. Then we can improve it. That's it. So let me make it precise. So in order to make it precise, I'm writing this polarization tensor in 2 dimensions in different way using sine and cosine. Okay. And now, suppose the conductivity is radial, then we have this cosine sine term is switching. Decoupling term is all 0. So the remaining one is only this one. So if it is a radial, then we have this expansions. And using these expansions, we can get the very important 2 formula. Suppose I'm designing like this. So here is gamma 0, and this is gamma, and this is 1. Okay, and this is radial. And then you dilate just to dilate the conductivity. So if you dilate it, then on the radius of low, it is gamma 0, and the radius too low, it is gamma, and outside it is 1, right? Now, you make a full asymptotic expansion of this Dirichlet-Neumann map. Okay, then it is given by this. These are high-order generalized polarization tensors. Okay. You can derive it. If you suffer a little bit, then you can derive it. Okay. Now, these polarization tensors satisfy this estimate for any order. Okay. Now, what can you do? Suppose, so the GPT vanishing structure of order n means the general polarization tensor up to order n is 0. So our summation formula becomes like this. But these ones are less than 2 to the 2k, so we get this. That's it. This is an enhancement of the near-cloaking up to this order. Now, then question is there such a structure? Can you design a structure whose the polarization tensor up to order n vanishes? And to see that, we make a multi-layered structures. Okay, and then so radius is to be determined, and the conductivity is to be determined. And you do all these computations. These are transmission. This comes from the transmission conditions on each interfaces, and then you end up like this. All the multiplication of all the transmission the conditions gives us this one. And what we want to do is so we want to find these sigma j and rj, so that this product of the 2 by 2 matrix becomes upper diagonal. All right. If n is 1, we already know the solution, and we can write down the equation, and you can see that there are a bunch of solutions, infinite number of solutions. N is equal to 2, I can do that. N equal 3, maybe one afternoon with a cup of beer, I can do that. N equal 4, oh, I don't think I can do that. So in general, this is highly nonlinear, high order algebraic equation. And want to determine, we want to prove that there is a solution. We couldn't prove it. Couldn't prove it. Okay. But again, this is our inspiration. So instead, we try to construct the solution using numerically. Okay? This is a numerical solution. So this is conductivity. Conductivity, background conductivity is 1, and outside it is 1 and fluctuating 1, and so higher than 1 and then less than 1, higher than 1 and less than 1, and so it is killing. In this way, it is killing the generalized polarization tensor. Look at this polarization tensor. This is 10 to the minus 15. I would say it is a 0. Okay? So up to 3 is 0, and the other ones are large. So how about 6? So it is fluctuating, and this is something like a 10 to the minus 13. So it exists. I'm pretty sure that there are infinitely many of these solutions, but you couldn't find any one of them. I mean, by hand. Again, this one is 9. So in this case, is the conductivity of the core. This part is fixed to be 0. Okay. Then you have this solution. Again, solution. Okay. So let me make some comment. So in order to kill the generalized polarization tensors of lower order, this structure must be fluctuating. Okay? So question is, suppose you increase number of the fluctuation, n goes to infinity, then it should go to the perfect cloaking. Then can you prove that the limit exists or things like that? I think it's a very, very interesting question, I believe. I still have 10 minutes, but I have only 2 slides. But the other slide is a thank you, so I have 1 slide. So using GPT vanishing structure, we can improve near-cloaking effect to this much, which is dramatic, I think. And also, if you are just interested in far field measurement, the measurement, then you don't have to transform. Okay? You just make it the core and then coat it with this structure. Then far field, don't see it. Okay? But if you want a near field the cloaking, then you have to transform it. Okay? So the problem is we couldn't prove yet is existence of GPT vanishing structure. This is I think this is mathematically, this is quite interesting question. And what is the limit of GPT vanishing structure when n goes to infinity? And I said the coming attractions. This is, but the Habib's student Bang Sang Jognong, he computed all these things numerically, tested numerically, and so the result is wonderful. So next time I can show you. We are writing it there. And also this result has been, we extended it to the Helmholtz equation for the far field, I mean, in terms of the far field measurement. Okay. And also, this is maybe I had 10 minutes, I can show, this is anomalous, so-called anomalous, the cloaking by the anomalous localized resonance done by the Graham Milton and the Nikolov and these papers, and we set up mathematical framework for this. So next time I can show you, but maybe not. Okay. Okay. Thank you. Yeah.
Any questions?
So when you have a given object that you want to hide, and then you want to put this enchantment around it. I mean, when you have some given object that you want to hide,
Yes.
that have, say, like you know, it's 3 polarization tensors. I mean, so the layer that you put around it depends on this object that is inside.
Not really. It's, so suppose you just insulate this core. I mean, this is I don't know whether this is practical, but I mean, for the conductivity case, you just insulate it, but then nothing goes in. So whatever you put inside is okay.
When you said you think there are infinitely many solutions, you mean your R's are free and your gammas are free to be?
Yeah, both of them. If the R is fixed, then I think not many solutions. So both of them are free. Then I think there are infinitely. For example, the Hessian's neutral inclusion, it has infinitely many solutions.
I have a second question. For the enhancement of your cloaking of your co-author, what was capital N?
Capital N? Oh, capital N corresponds to the number of GPTs, order of GPTs to be vanished, and that corresponds to the number of layers. Yeah.
I was making a joke. You know, you showed your co-author enhanced cloaking.
Yeah.
What was capital N for that?
Good question. Good question. Maybe 100.
Okay. No other question? Then thank you again.
That's